how would I implement the constraints to vary from element to element? This is going to start getting messy. This is why we use hierarchic bases. How are you going to make all of this algorithm work when you don't have this uniformity of approximation? And that's a problem I turned my attention to last year. And that's what I was going to talk about today until I realized that it's kind of a lost unless you know that all this stuff that's going on in the background. The result is, and this can be found on a technical report on the Brown web page, is that non-uniform order can be done just as efficiently as uniform order using Bernstein bases in any number of dimensions. You can have a completely arbitrary polynomial distribution, and all of the results I've shown you here for the uniform order case carry through. Now, that wasn't clear at first. I mean, first of all, how do you even define the space? So basically, you go back to topology, you know, I mean, it's all about topology, breaking up these meshes, simplicial meshes in any number of dimensions into topological entities. You then assign a polynomial to each topological entity. And these Bernstein polynomials are completely determined by the entity with which they're associated. Once I'm on a face, I can work out the Bernstein polynomial on that face without looking outside. Once I've got it on the face, there's a natural extension of that Bernstein polynomial onto any higher order simplex, of which that's a subsimplex. This means that I can just decompose my simplex in d dimensions into a direct sum of simplices in lower dimensions, assign a polynomial order to each simplex, Bernstein polynomial each of them, put it all back together, I get the full space. Arnold, Falcon, Winter did that. The same thing works in a non-uniform order case. So there's the non-uniform order basis. It's naturally conforming. So the question, the stick that I've been beaten with, how do you change the order locally without affecting the number of nodes, is now a non-issue.